Hi. In the previous video, we discussed about the derivation of shape function related with the heat transfer in 2D dimensional element, isn't it? And in this second video, we are going to discuss about the same derivation of stiffness matrix, that is K matrix for triangular element. As usual, in the xy coordinate, we are having the triangle node having the nodes 1, 2, 3 and their respective coordinates x1, y1, x2, y2, x3, y3, and the temperature T1 at node 1, T2 at node 2, and T3 at node 3. Here, consider the three noded triangular element with the nodes temperatures T1, T2, and T3. The temperature function is given by T of x comma y is equal to n1 T1 plus n2 T2 plus n3 T3. Already we know the shape function in the of triangular element n1 is equal to a1 plus b1x plus c1y. So n3 is equal to a3 plus b3x plus c3y divided by 2a. We know the stiffness matrix Kc, that means stiffness matrix for heat conduction, right? Kc is equal to integral bt dB into dV. Already we know the strain displacement matrix B matrix is equal to dou n1 by dou x plus dou n2 by dou x plus dou n3 by dou y, dou x, and dou n1 by dou x, dou n2 by dou y, dou n3 by dou y. By partial differentiation, we are going to differentiate all those values. We will get it as each values dou n1 by dou x up to dou n3 by dou y. And here we are having the B matrix. After making the partial differentiation of the each shape functions, we will get it as a B matrix as 1 by 2a into b1 b2 b3 c1 c2 c3, and by taking that B transpose 1 by 2a into, as usual, b1 c1 b2 c2 b3 c3. So stress strain matrix D is equal to kx0 0 ky. So assuming a unit thickness, the elemental volume can be expressed as dV is equal to dA, right? So this is the important condition. Substitute the above value in Kc, that is stiffness matrix for heat conduction, is equal to integral bt dB into dV. So we are applying those values, and Kc is equal to, so we will solving all the terms by using the matrix multiplication. We will get the huge size, that is Kc is equal to 1 by 4a into, so some terms are there. And to determine the stiffness matrix for convection, so in this video we solved, in this slide we discussed about the Kc, right? But here we are going to discuss about the stiffness matrix for convection, that means Kh, right? So stiffness matrix for conduction is Kc, and stiffness matrix for convection is Kh. So that is surface integral h into ntn into ds. So it's a standard equation, already we know that. Therefore we are applying that n shape functions, and again we are making the matrix multiplications. Here very important thing is there, let the edge 1 2 of the triangular element, the edge 1 2, that means node 1 to node 2, that particular edge 1 to 2 edge, that edge is having, it was shown in the next figure. So n3 is equal to 0 along this. So here just go through edge 1 to 1 to edge, we are having some convection, right? So here substituting n3 as 0, okay, kh is equal to, so n3 is going to be 0, so we will have a reduced equation, and here we are substituting the remaining terms. We will get the kh is equal to h into surface 1 to surface 2. Again we are having the some terms in terms, right? And after solving those things, we will get the value of integral L2 square ds is equal to s by 3, and integral L1 L2 into ds is equal to s by 3. Substituting these values in kh, we will get kh12 convection, stiffness matrix for convection at the edge 1 2 is equal to h12, right? So we are representing that edges, so that's why here they will clearly mentioned it, okay? So h12, so the edge 12, okay, and we will get the value k is equal to hs by 6 into the same equation, but here we are representing the edges 1 2, so h S12 S12 divided by 6 into 210 120 000. Now we are considering the edge 2 3. So what will happen in 2 3 edge? So it is going to be changed as H KH12. Instead of 1 2 we are applying the edge 2 3. So KH23 is equal to H into integral S2 to S3. Okay. So again we are solving those equations. So we will get the equation as Hs by 6. So Hs by 6. So H23 S23 divided by 6 is 0 0 0 0 0 to 1 0 1 2. Right. So if you go through these two equations, especially in this equation, I am going to discuss about some important peculiar similarity here. It is a edge 1 2, so that these two are having the values, my dears. But here it's a third row, third column, isn't it? So it is going to be 0. While the meantime, just go through in this particular equation here, we are discussing about the edge 2 3. So here second row, third row, second column, third column, we are having the values. Then the related first column and first row is going to be 0, right? So these are some shortcut to remind these equations in our mind. And finally here we are going to discuss about the edge 3 1, edge 3 1. So KH31 is equal to, as usual, H into integral S3 to S1, which is going to be solved, and finally we will get the value as KH is equal to HS by 6. That means H31 S31 divided by 6 into 20100000102. So like that it is going to be here. Here the involvement of the surfaces, what are all they? That is 1 3 or 3 1. So first row, third row, first column, third column will be having the values, but the remaining that term which is having this 2, so that means the second row, second column is going to be 0. Just to go through that similarity here, it is going to be the middle rows and middle column are going to 0. Here we are having the this particular first row is going to be, first row and first column are going to be 0. Here we are having the third row and the third column are going to be 0. So which edge is not be considered, that is going to be 0. So simply we may say it as, okay. So that's why the conclusion is, therefore KH stiffness matrix for convection is equal to, so we are assembling all the values. KH is equal to KH12 KH23 plus KH31. So we will get the large size of the equation. So here again we are reducing for our convenient. KH is equal to, so but actually stiffness matrix for the CST element K is equal to Kc plus Kh. That means stiffness matrix for conduction plus stiffness matrix for convection. So we are adding all those values. We will get the simplified equation. We will get the equation as like this. Okay. So during solvation of the problem, they will clearly state the boundary condition. So by that boundary condition, we will easily sort out this entire huge size of the equation into our feasible or our conveniently we will solve it. So in this equation the boundary condition is very very important for proceeding in further manner. Thank you. In the next discussion we are going to discuss about the derivation of the force vector, that means load vector F of the heat conduction. Here F1 is equal to Q naught NT into dV, that is the equation. So here we are applying the shape function values, and as usual we are solving it throughout the problem. Over here we will get that F1 is equal to Q naught A divided by 3 into 1 1 1. Okay, and F2 is equal to Q12 S12 divided by 2 into 110, and F3 is equal to HT12 Ti infinity S12 divided by 2 into 110. So F1, F2, F3 values are finally concluded here. That means force vector for the heat transfer two-dimensional element. So thank you so much for your patience of the video.